All right, my dear children, we go to the last type of nuclear reaction. Okay, that is called nuclear fusion reaction, or we can simply call as what? Nuclear fusion. Now, fusion means to combine, but the combination of what? A lighter nuclei. So, lighter nuclei can combine to form heavy nucleus. And under this case also, okay, what happened? The energy will liberate it. But remember, children, the lighter nuclei cannot combine or fuse together at ordinary temperature. This usually occurs at a very high temperature. Okay, so we can now come to the definition of nuclear fusion. So nuclear fusion is a reaction, nuclear reaction, okay, in which two or more very light nuclei, see I am using the word two or more very light nuclei, moving at a very high speed, if they fuse together to form a single nucleus or heavy nucleus with the production of huge amount of energy, and such process is called nuclear fusion. So children, we can now simply define the nuclear fusion as the process of combining two or more very light nuclei moving at a very high speed fused together to form heavy nucleus with the liberation of huge amount of energy or tremendous amount of energy, and this process is simply called as nuclear fusion. Simply called as what? Nuclear fusion. But the question arises out here is that why again the energy will be liberated when the two lighter nuclei combine to form heavy nucleus? It's because the mass of the product nucleus, okay, in the reaction will be always less than some of the masses of the nuclei, or also called reactant, which are fused together. So when lighter nuclei combine to form heavy nucleus, okay, there will be a loss in mass, and this loss in mass is actually converted into energy as per Einstein's energy mass energy relation, and this energy is also known as nuclear energy or nuclear binding energy. But we observe this nuclear binding energy in the form of heat and light also. Okay, that's why we also call this energy as thermonuclear energy, or also called radiant energy. Like, let me give you one example, children. Okay, sun gives us heat and light. Stars also give the light. Okay, it's because of the fusion reaction. Okay, because sun is simply a glowing mass of gases, mostly hydrogen and helium, and these gases fuse together at a very high temperature and pressure, and due to that fusion, the energy which continuously receive from the sun is in the form of heat and light. Okay, heat and what? Light. That's why the nuclear fusion reaction is mostly observed, okay, in the sun, stars and all. Okay, sun and stars and all. Okay, that's why the energy, as I said, the release in the form of in nuclear fusion reaction is actually due to the mass defect. The mass defect means the product of the mass of the product nucleus is always less than the mass of the what? Mass of the reactant. That means the lighter nuclei which fuse together. That's why the loss in mass appears in the form of what? Energy. Or get converted into form of energy. Okay, so this is the statement of nuclear fusion as a reaction. Now we have a number of simple reaction that can be observed, okay, as a nuclear fusion reaction. Now for that, let me just go with one of the example of nuclear fusion reaction. Now, if one of the isotope of hydrogen, and this isotope of hydrogen is deuterium, if one deuterium combined or fused together with another deuterium, you know deuterium is a lighter nuclei, and these are the isotopes of what? Hydrogen. These are the deuterium. Deuterium means nothing but the isotopes of what? Isotopes of hydrogen. So one of the deuterium, if I combine with fuse with another deuterium, okay, then what will basically produce? Another isotope of hydrogen will produce, that is called tritium. This is called tritium. So once tritium is formed, along with tritium, one of the isotopes or hydrogen, that is H11, the hydrogen atom is also formed. With that, the energy get also liberated, and almost 4 mega electron volt energy will liberated. And children, this energy which liberated is in the form of the energy of this particle, the kinetic energy of particle, and even the energy of heat, and the energy of the heat, okay, and even some rays may also produce. Okay, some rays also produce. But this tritium, okay, so formed can further fuse immediately with the third tritium. That means this tritium so form on the in these two fusion of these two lighter nuclei will further fusion with another deuterium. So once it further fuse with another deuterium, then what will basically form? Another particle will form, that is called helium nucleus. Along with the helium nucleus, the neutrons will also emit, and along with that, the energy will also get liberated. So almost 17.6 mega electron volt energy get liberated. Energy get what? Liberated. Okay. So under this case, if you see total how many deuterium atoms, isotope hydrogen are fused together? 1, 2, 3. So that I can write the net reaction. So that I write down the what? Net reaction as H12, H12 and H12. So total how much? 3 deuterium atom if they fuse together, okay, to form what? To form H11 plus He24 plus neutron. Along with that, the total energy which is liberated will be how much? 21.6 mega electron volt. Because this tritium simply cancel out. Okay, so that's why the net reaction that can occur under this example for nuclear fusion is the fusion of 3 deuterium atom combined to form helium, hydrogen atom along with the neutron, and with that what is liberated? The energy is liberated. So look at the energy which is liberated. So if you add this two, it will be 21.6 mega electron volt. So the total energy of 21.6 mega electron volt get liberated. So the energy released per deuterium is calculated as, so I write down just the energy release per deuterium is simply 21.6 mega electron volt divided by 3, because there are total how many deuterium atoms they are fused together and release energy 21.6. So if I calculate the energy released per deuterium, so it will be almost how much? 7.2 what? Mega electron volt. Okay. So most of the energy that you can see, liberated energy, appears in the form of kinetic energy of this neutron, proton and all. But other than this energy, okay, the energy which is liberated can also be observed in the form of heat energy, okay, and also observed in the form of energy occurred by some radiation also. So this is one of the good example of the nuclear fusion reaction which takes place. Now there is alternate example that we can see also for the fusion reaction to take place. So let me just go back to alternate example also. So in alternate example, we can even see the fusion of 3 deuterium takes place into alpha particle. So for that H12, if it fuses with H12, it can even liberate under certain condition as one of the unstable isotope of helium, that is He23. Along with that, neutron may also produce, and the energy which also liberated 3.3 mega electron volt. And this unstable helium nucleus He23 can further fusion with another deuterium to form helium nucleus plus proton plus how much energy? Almost 18.3 mega electron volt energy will be liberated. So under this case also, if you calculate the net energy, net reaction which takes place, is also the fusion of how many? 3 deuterium atom, H12, H12, H12. So when 3 deuterium atom fuse together to form what? Again same, the heavy helium nucleus plus neutrons will liberate, the protons, okay, will also produce the hydrogen atom, and you can see the energy which liberate also is how much? 21.6 mega electron volt. That means this net result is same as this result. So energy released per deuterium outer is also 7.2 mega electron volt. Okay, so this is one of the good example to understand nuclear fusion reaction. Now children, one thing we can observe in this reaction, that the energy, total energy which is released in a fusion reaction, that is how much? 21.6 mega electron volt. Now this energy output in a fusion reaction, that is 21.6 mega electron volt, is very much less is very much less, as you see if you compare with the energy release in a fission reaction. And you know, in fission reaction how much energy was released? 200 mega electron volt. Now this energy is 21.6 mega electron volt, which is much less compared to the energy released in a fission reaction of uranium, that is 200 mega electron volt. But it doesn't mean that the fusion reaction is weaker energy source than fission. The reason is that the number of deuterium in 1 gram of heavy hydrogen, that is called deuterium, is much large compared to the number of what? Uranium 235 nucleus. That is in what? Also how much gram? 1 gram. So if you compare 1 gram of deuterium and if you compare 1 gram of what? Uranium 235, means the number of atoms, okay, the number of what? Deuterium atom present in 1 gram of H12 is much large compared to the number of what? Atom present in 1 gram of what? How much? 235. Okay, and due to that, as a result, the energy output, okay, by the fusion of 1 gram of deuterium, okay, fusion of 1 gram of deuterium, 3 deuterium atom with 1 gram of deuterium, okay, is much large compared to the fission of what? 1 gram of what? Uranium 235. That's why the fission reaction in which the energy which get liberated is very large compared to the energy which is released in fission reaction. That's why when fusion reaction takes place, a tremendous amount of energy get liberated. That's why just imagine that in sun what happened? What type of reaction takes place? Fusion reaction takes place. And due to that fusion reaction, the tremendous amount of energy which generated in the fusion reaction of sun, and that energy can come out in the form of heat and light, and the form of radiant energy also we call as radiant energy, also called thermonuclear energy, and that energy we continuously receive from the sun on the earth. Now the last part of this nuclear fusion reaction that we now discuss is that the difficulties in nuclear fusion. Yes, in actual practice, the nuclear fusion reaction is very difficult process. In actual practice, nuclear fusion reaction is a very difficult process, since the nuclei to be fused are positively charged. Like you saw the nuclei like H12, okay, this has to be fused, and both are what charged? Positively charged. Okay, and this charge, positive charge, acquire a repulsive force, a strong repulsive force between them. So that's why they must be brought very close to them in order to fuse together. Okay, not only at a high pressure but also at a high kinetic energy and also at high temperature. That's why for this reason the temperature must required for the fusion reaction to take place must be in the order of 10 to the power 8 Kelvin. Look at the range of temperature or the order of temperature that is required to make a fusion reaction to take place in actual practice, because at this temperature and high pressure only the two lighter nuclei, okay, can fuse together. That means in actual practice the fusion reaction is a difficult process. Okay, so look at this temperature. The temperature of the order of 10 to the 8 Kelvin is required, and such temperature is only available in sun and stars. Only available in what? Sun and stars. So these are the temperature that can be available in sun and what? Stars. Not on earth. Not on what? Earth. That's why on the earth they may be produced by exploding nuclear fusion bomb. That means fusion reaction, in order to observe fusion reaction on earth, okay, what you need to do? You need to explode what? Nuclear fusion bomb. And when nuclear fusion bomb explode, then definitely tremendous amount of energy will get liberated. The temperature become very high, and that temperature can be used for the fission of lighter nuclei. But this is not possible on earth, because once the nuclear fission bomb is used, it can destroy everything. Okay, that's why the nuclear fusion cannot occurs in what? On the earth. Okay, so nuclear fusion reaction although occur in sun and stars, and these are the natural process, is a natural reaction only, but in actual practice it is not possible. That's why a very high temperature and pressure are needed for the fusion of lighter nuclei to take place. And this process is also called as thermonuclear reaction. So nuclear fusion reaction is also called thermonuclear what? Reaction. Now the word thermo means heat. That means there is those nuclear reaction which can occur at a very high temperature only. And that nuclear reaction is a nuclear fusion reaction. That's why nuclear fusion reaction, which require very high temperature, is also known as thermonuclear reaction. And the energy which released from the reaction is called thermonuclear energy. What energy we call? Thermonuclear energy, and we also call this energy as radiant energy or solar energy. Okay. So this is one of the important point that you need to keep in mind, that nuclear fusion does not take place at ordinary temperature. It's not possible on the earth. Okay, once if you do this fusion reaction, observe this fusion reaction, if you observe on earth, means there must be a nuclear fusion bomb to be exploded, and that can be utilized for the fusion of lighter nuclei to take place, but it is not possible. Okay, so I've explained in detail about the nuclear fusion along with the difficulties in nuclear fusion. Now we do some numerical problem from this chapter, or two numerical problems we solve from this chapter. So with that, the chapter get completed.